Hi, everyone. Today's video is going to focus on the periodic table, which is a nice summary after the color coding periodic table that you should have already completed. And so we'll talk a little bit about the history and the origin, but most importantly, the categories and groups and some of the terminology that we'll use throughout the rest of the year. So a little history. Dmitry Mendeleev was a Russian scientist who first started to piece together the arrangement and the puzzle that is the periodic table. And it was originally arranged by reactivity. So in general, the elements are grouped together by a lot of their properties. And so they realized that if certain elements reacted really violently with water, they put them all into one column. And if elements reacted in exposure to air, they put them in a different column. And this actually wasn't too far off from what we know in the periodic table today, but there's just a better way to arrange it so that there's a more systematic structure. And we'll get into that here in just a minute. Some of the terminology that we regularly use, although sometimes I still refer to them as rows and columns, but the reason that the periodic table gets its namesake is that they referred to the rows as periods, kind of like a period of time. So at the beginning of a period, at the end of a period, there is a certain pattern to the structure of those elements. And then the columns, because they were grouped together by property, are oftentimes called groups, or sometimes you'll hear them referred to as families, like a family of a certain category of elements all behave one particular way. All right. And that is really important to remember, that the placement of the elements in the periodic table is intentional. So if you have elements that exist within one group, they're all going to chemically react similarly, just have like maybe a different time that it would take for the reaction, or a different amount of energy that's associated with that reaction. Okay. Today's periodic table, the modern periodic table, is arranged by increasing atomic number, right, which is really referring to how many protons are in the nucleus of the atom. Right. So we start always our periodic table in the top left corner with element number 1, and then it cuts to the right over here with element number 2, and that's the first period, just those two elements. And then we start back kind of like whenever you hit enter on a keyboard and you go down to your next line. We've got element 3, element 4, 5, 6, 7, 8, 9, 10, and so on. And it keeps going in that kind of left to right pattern as you go down the periods on the table. Right? We now know that the periodic table itself is broken up into 3 major categories. The majority of the periodic table are made up of metals, and then there's a smaller section in the top right corner of nonmetals, and then this barrier of elements that separate between the two that we refer to as metalloids. Right? So some of the properties that we know after the reading of metals, one most common one is that metals conduct electricity. Okay. They have a really good job, just like wires that run the electricity through your house are made up of metal. They do a really good job of being able to pass electricity quickly from one area to the other. Another property of metals is that they are malleable, which means you could kind of hammer them down into different shapes and pieces. If you think about a blacksmith hammering like iron into different shapes, or over the anvil of like different tools and whatnot. Not necessarily a skill utilized a lot today, but metals have that bending, malleable property to them. And then the last most important one is that they regularly donate electrons. So in the next unit, when we start talking about how these atoms are going to start chemically reacting and exchanging materials with each other, the metals are our electron donors, and then the opposite to that, our nonmetals are our electron acceptors. Okay? So a little bit of a kind of an opposite story. Nonmetals don't conduct electricity. They're very brittle, which means you can't really bend them and shape them into the pieces that you want, and then they accept electrons. And this isn't 100% like hard and fast rule. There are a few exceptions here and there, but this is the most common trend for those 2 major categories in the periodic table. And then the metalloids, have kind of dual roles. They have both metallic and non-metallic properties. One good common example of a metalloid is silicon, which you've heard of, like in terms of like Silicon Valley. So they use silicon in computer chips, where you can kind of shape them into the piece that they want. They conduct electricity really well, like metals, but they don't heat up, and they have some non-metallic properties to them as well. Okay? Some of the more popular names for groups on the periodic table, as you see them kind of referenced in some readings or online. Group 1A, the very first column in the periodic table, are what we call the alkali metals. And then just to the right in group 2A are the alkaline earth metals. In group 7, as we jump close to the far right of the periodic table, but not the furthest to the right column, we refer to that group as the halogens. And then group 8A are our noble gases. And so the actual meaning behind those names doesn't really hold a lot of reference yet. But as we go further throughout the year and we make reference to the alkali metals and their properties and the noble gases and their properties, there's a little bit more of a connection as to why those are categorized and given those specific unique names. All right. Group B is a little bit of a mystery, only because there isn't a good indication in your periodic table where that lies. And so I want to tell you that the name for group B is called the transition metals. And when we move back up to the top of this sheet and we take a look at that blank periodic table, I'll do a better job of explaining where that's exactly located. All right, and then lastly, we only have a handful of metalloids on the periodic table, and those are all collected over there to the right. The main thing that I like to reference is that these elements make up the staircase, that zigzag darkened line on your periodic table. So they're kind of the separation elements that keep the metals on the left side and the non-metals on the right side. And so if we go back up to the top of this document and we look at our blank periodic table, again, our metalloids kind of run along this zigzag pattern. We've got predominantly all metals on the left side of the periodic table, and then a smaller collection of non-metals in the top right corner of the periodic table. And then there's one little exception. We've got hydrogen over here. Even though it's on the left side and it's over group 1, hydrogen is a gas, and there are no naturally occurring metals that exist as a gas. So this technically belongs over here in the non-metal group, but based on the way that hydrogen reacts and behaves, it's always drawn on a periodic table over group 1. Okay? So how many periods are there specifically on the periodic table? Periods referring to the rows. We technically have 1, 2, 3, 4, 5, 6, 7 periods. And you're probably wondering, well, what's the deal with these 2 rows down here? That's kind of like a cutout. If you think about a map of the United States of America, and Alaska and Hawaii technically are our last 2 states, and they're always drawn really close to Washington and California, but geographically they're very far away. And so there's always a little cutout that shows them as a part of the country, but the map doesn't really do justice as to how far away they are. So these 2 bottom rows technically need to be inserted right into here on the periodic table. And so the entire right side of this periodic table would have to shift over, and then these 2 rows would be inserted in. The reason that we cut those 2 rows out is because if we had to stretch the periodic table as wide as it actually is, it'd be really small to get all of the little detail of the numbers and the letters into each box. So it makes it a little bit more of an organized image to have it cut out and pulled out to the bottom. Okay, so I'm going to clean up the periodic table here. And then when they talk about how many groups, again, groups meaning how many overall columns there are. We've got what we call the main group elements, and that's all of these on your periodic table that are marked with an A. Okay, so that's like the A group, the ones that have a specific property or trend that runs throughout that entire group. And so there's 8 of those, 1A, 2A, 3A, all the way over here to 8A. So we're going to say that there are 8 A groups. And then this entire section here in the middle doesn't belong to the A group, and we refer to that as the B group. And the name for that B group down in the bottom left corner of this page is the transition metals. Okay, so we've got 8 A groups and then 1 large B group. And again, they're still categorized as metals, but the properties and behaviors of that inner rectangle of metals is pretty unique. There's not one consistent consecutive pattern, and we'll spend a little bit of time just talking about how the transition metals are different from the other metals. Okay? So for the next question, it says both alkali metals, which we have to recall as group 1, so right here, and the halogens, which is group 7, right here, are very, we're going to say, reactive. Okay. Each of those 2 groups, elements, react very, very regularly with other elements, with water, with the air that they're exposed to. And it has a lot to do with what we're going to spend some time talking about in the rest of Unit 3. It has a lot to do with their atomic structure. Okay, so I'm going to talk about the next question, and then I'm going to pull up an image that'll give us an idea of why those elements are a little bit more reactive than others. And then group 8A down here, the noble gases, right? That's the last column on the periodic table. The reason that they're called the noble gases is that they are very unreactive. Right? They got the title noble because, back in, the times of kings and queens, the nobility didn't interact with the townspeople. They had servants do all of their bidding. And so the elements in that last group, group 8A, don't react. They don't mix with other elements very easily. So they behave very noble-like. They don't want to share their electrons or their subatomic particles with anybody else. Okay, so I'm going to click on that link and bring up this image here. I'm going to drag it over. This is one of the models of the atoms that we talked about in the last video. So this is the periodic table of the Bohr models. And so we've got hydrogen in the top left corner, and it kind of takes the same spacing as everything else. And then you notice here in the middle, in that blue vertical rectangle, that's the cutout for the transition metals. And you'll notice that as you move down to the second row and to the third row, there are additional rings of electrons that are added. And so if you completed the virtual lab where you built an atom, this is very reminiscent of those shapes that you saw as you added in protons and electrons to your made atom, right? So I want to focus on the first group, hydrogen, lithium, and Na, sodium, all the way on the left-hand side, and then the 7th group that just has fluorine and chlorine, and talk about why those are so reactive. You notice how lithium has only 1 electron in its outermost ring, and sodium also has only 1 electron in its outermost ring? Well, the inner rings that are completely filled up have a really strong level of stability. And so it doesn't take much to rip that 1 final electron away from the lithium atom or the sodium atom and remove it down to its much more stable inner ring, right? And then if we move over here to group 7, where we've got fluorine and chlorine, we've got kind of the opposite story, where fluorine's outermost ring has 7 little blue electrons, and chlorine's outermost ring has 7 little blue electrons. And they're so close to matching up to group 8, that noble gas arrangement, that they only need 1 additional electron. So the fact that both the first group and the 7th group are very close to a stable arrangement of a complete outermost ring makes them so very reactive, because they just need 1 extra electron added, or 1 electron removed to get to that stable position. All right, and then if you look at the very last column, all the way on the right, we've got helium, neon, and argon. They have a completely filled in outermost ring, which we're going to talk about here in a bit as the valence shell. And that has a really strong level of stability, meaning that they can't take on any extra electrons and they don't want to give up any of their electrons. Okay. All right, so let's finish up the back side of the notes. We're going to talk a little bit more specifically about the atomic structure, right? And so the atom itself is the smallest individual unit of an element, and atoms have made up of subatomic particles, okay? So in terms of the individual atoms, if I had a bar of gold and I broke it down to its atoms, each of those atoms would still have the same properties pretty close to that bar of gold. But when I break down the atoms themselves into their individual protons, electrons, and neutrons, those protons no longer have the properties of the gold that they came from. So a proton from an oxygen atom and a proton from a gold atom will all look the same. Protons are the same. So it's really the makeup and the amount of each of those subatomic particles that makes an atom behave like gold, behave like oxygen, behave like the individual elemental properties that they have, right? So the first key term that we're going to talk about is atomic number, and that is the number of protons in the nucleus. And it's important to remember that protons are positively charged, right? Ernest Rutherford's gold foil experiment from the last video we talked about proved the existence that there is some positive component to these atoms and that it must exist in some densely packed nucleus because it had that kind of weird bending interaction with the radioactive material. All right, so in our image off to the right, we see a bunch of little plus signs on these orange subatomic particles indicating that we've got protons in there. But if they're all positively charged, we know that like charges repel. Like if you bring up two positive ends of a magnet, they're going to push off of each other. So there has to be something else in the nucleus that's preventing all of those positive pieces from bumping into each other and then reflecting away. All right, so that was that's what led them to the understanding of what we now know are these green atoms, these neutrons. Right, and neutrons are neutrally charged. I always refer to neutrons as packing peanuts or bubble wrap. You order a package, and when it's shipped to your house, they put a bunch of filler material in there, which isn't what you ordered, but it's there to prevent all the other pieces from bumping into each other, right? And so the total amount of protons and neutrons in that densely packed nucleus is what we refer to as the atomic mass, and that is the average number of protons and neutrons in the nucleus. Okay, so the common misconception is that students think neutron starts with an N, must be the negative subatomic particles, but neutrons get the name because it's the prefix of the word neutral. Right? Electrons are actually the first subatomic particle discovered. J.J. Thomson passed an electric current through his cathode ray tube, and because he used electricity and found a negatively charged particle, that's where they got the name electron, from the electricity that was used to discover it. Okay? So we need to be able to account for the number and the amount of subatomic particles within one particular atom. And so the way that we do that pretty easily is by drawing what's called a shorthand notation. And it's just a way to represent an element using the symbol, the atomic number, and the atomic mass, right? So off to the right, we've got a cutout box of something that you would see from the periodic table. And so you've always got the name, the symbol. Here's the name for chlorine. Here's the symbol for chlorine. And then if you look at your green periodic table that you got earlier, you'll notice that each element box has two numbers in it. And the smaller whole number always refers to the atomic number. Or you can't have a half of a proton or a tenth of a proton. You have to have a complete whole number of individual protons. And then this top number at 35.453 that's referring to the atomic mass. So that's a slightly larger number because that's the number of protons together with the number of neutrons contributing to the overall weight of the atom. Now you might be wondering why exactly that has a decimal notation, and that's because we have a bunch of different atoms that occur with slightly different weights, just like each of you in my class have different heights, and if I took the average height of a student, it'd be some decimal value. So this is always represented as an average mass, which we're going to talk about in our next video. But what we want to know is, given the specific number of neutrons or the specific mass number, how can we calculate the number of protons, electrons, and neutrons? And that's what we're going to talk about next, calculating what we call calculating PEN, which is just abbreviation for protons, electrons, neutrons. Okay? So let's start by writing the shorthand notation for this carbon-14 atom. And so the shorthand is starting with the element symbol, carbon. And then what we're going to always do is in the bottom left corner, we're going to write the atomic number. And then in the top left corner, we're going to write the atomic mass. Okay. So if I rewrite it over here, we start with carbon. And after you locate carbon on the periodic table, you'll notice that it has an atomic number of 6. And it also has an atomic mass of 12.011. Again, that's an average value, but in the question up here, it said to write carbon-14. Whenever you see that with a whole number following the element name or the symbol, that's referring to the mass of that particular atom. And so the mass that we're going to use for this shorthand is 14. Okay? That shorthand notation is standard. So we know that whenever we have a number in the bottom left corner, like the 6, it's referring to how many protons there are. Okay? And if we have an atom, just like we, again, experimented with our building the model, building the atom virtual lab, in order for it to be a neutral atom, no charge, the number of positive protons has to be canceled out or evened out with the number of negative electrons. So at this stage in the game, we're going to say if there's 6 protons, there have to be 6 electrons. And so we know that protons equals the atomic number, electrons equals the proton number, and then the last subatomic particle, neutrons, has to be the mass number, which we're told for this particular notation is a total of 14. And remember, that's protons plus neutrons. And so if we subtract out the 6 protons that we have, what we're left with is the number 8 neutrons that are also in the nucleus of that atom. Okay? There'll be a worksheet that looks a lot more complicated and busy than what it actually is. It's a big table that we're going to have you go through and diagram the PEN, protons, electrons, and neutrons of various atoms for your homework.